So we're ready when you are, Leo.
Can you see my screen?
Yes.
Okay, cool. So, well, for today's protocol onboarding, we are going to be chatting of runtime basics and in particular, like everything that's needed to like run contracts. So running them. Uh, Feel free to interrupt me literally anytime. I'm not going to be able to read the Google Meet chat because it does not appear on my screen, as you can see my whole screen. So just raise your voice, and if I don't hear you, yell or something. Uh, so feel free to interrupt me anytime. If there is anything you don't understand, or if there is anything that I say that you think is wrong, like it's possible that I've made mistakes in my presentation. So some people know better than I in this room about some of the things I'm speaking about. So like if you think I'm wrong, say it and we can speak about it. So the first thing is like, what is a contract? So our contracts are written in languages that are compiled to WebAssembly. So from the near core point of view, we execute WebAssembly contracts. And like everything else, like whether it's be Rust or JavaScript, is entirely independent of us. Like it's some things that happen before anything ever reached like the blockchain. So what is WebAssembly? So WebAssembly is a bytecode language. So when written in textual form, it's a Lisp-like stack-based assembly language. So reverse reverse Polish notation in a Lisp-like language. We will see more example about that later. It is a compiled target of Rust-C, which allows us to write Rust contract under the name WASM32 unknown. And it can also be transpiled from JavaScript to WASM, so used by near SDK.js. So just so you know, like that transpiling is based on QuickJS, which takes a JavaScript and compiles it to C, and then Clang that compiles to WASM32 unknown. So these are currently the two targets that our SDK supports. Before we also supported assembly script. I'm not entirely sure whether we still do. So like as far as I know nowadays, we are mostly supporting Rust and JavaScript. All of these targets compile to WebAssembly. So as soon as that compilation is done, and that's done by the contract developer, like nothing else matters to us. It's all like one WebAssembly contract. That's the thing we're going to be executing. And I actually hear the Google Meet message ping, so I can have a look or someone can speak. I don't know.
Hey, this is Yoon. I'll just quickly ask a question. So hypothetically, is it possible for someone to write something in a different language that's not JavaScript or Rust and compile that in WebAssembly and run it on like near as a smart contract?
Yes, it is possible. Like
Okay.
literally every language that can compile to WebAssembly can be run on the Near blockchain. This means like people can write contracts in C. People can write contracts. I think Python can compile to WebAssembly, so people can write contracts in Python, and like basically any language supported by LLVM. So I don't have any examples like right now, but any language supported by LLVM other than Rust and C can also be compiled. Well, C++, obviously, can also be compiled to WebAssembly and executed on top of our blockchain. However, we don't give any libraries for that, and so it would not be a nice user experience to do. So we'll see examples later, and you will understand why like it's not obvious. Like, let's say the libraries are important in order to have a nice developer experience. But theoretically speaking, yes, people can. And that's actually how we did it with JavaScript, which was not supported and then was supported without like any changes to NearD, because like the Near SDK team just developed Near SDK.js, and it uses the same host functions. We'll talk about that later. And it just works the same. Okay, so this bytecode gets executed by the WebAssembly virtual machine, which is like similar to a virtual machine. It has its own address space, its own stack, and that's the thing that executes the bytecode. So by definition, it is completely sandboxed. Like one WebAssembly, so long as the WebAssembly virtual machine does not have bugs, obviously, but one contract cannot affect anything outside of the WebAssembly virtual machine, because the semantics of WebAssembly are defined in terms of this operation does this on the virtual machine. So the issue is like we actually want to do things that are not sandboxed. We also want to like make token transfers. We also want to access storage. And all that is not defined by the WebAssembly virtual machine. The WebAssembly virtual machine literally only defines execution. So to do that, we have access to host functions, which allow it to actually do interesting things. And we will see examples of that later. I introduced a link to the spec so that they are in the slides. There is certainly way too much information in there. You probably don't have to care, but this way the link is easy to reach as soon as the slides will be online. So
just a quick question.
yes,
On the previous slide. So in Rust and in JavaScript, you can do plenty of things like networking or reading from the local storage or whatever.
Mhm.
How does, like, what happens to those, I don't know, invocations of the operating systems, I suppose, when we cross-compile to WebAssembly and then when we try to execute it? Because this is something that like shouldn't take place in the virtual machine, right?
yes, you're right. So this is actually what WASM32 unknown means. So basically, when you for JS, I will only be speaking about Rust because JavaScript is the same. Like we take the JavaScript contract, we compile it to C, and then we compile it to WASM32 unknown. So it's basically the same behavior. But what WASM32 unknown means is we compile to the WASM32 architecture, which is this bytecode, with operating system unknown and ABI for function calls unknown, which means that we have no access to the operating system and no access to dynamic libraries. So what other compile targets would be like x86-64, so like the usual Intel 64-bit architecture or AMD 64-bit architecture, dash Windows dash MSVC. So access to the Windows operating system function calls and using the MSVC compiler like function way of calling functions, or x86-64 Windows GNU EABI for Cygwin compiled, or x86-64 Linux GNU EABI. So that's what like this means. And so what will happen if you try to use access to use the standard library in a contract is it will not actually compile, because Rust does not know how to like take this system call and execute it on an operating system that is unknown.
Does it mean that we also cannot use any, like in Rust, it would be crates that at any point depend on like this OS support or the ABI that you mentioned?
Yes. So it means
That's
that
a
we
shame.
are limited to only no STD crates. Thankfully, Rust is starting to get quite a good ecosystem of no standard library crates. And with the split of allocation outside, so between core, which is available everywhere, and libstd, like the standard library, there is alloc, which allows to do allocations with vec and box and stuff like that. And with that, like with only core and alloc, lots of crates are able to work nowadays. So that does not mean every crate will work, because lots of crates are still designed with only like STD use case in mind. But most big crates in the ecosystem that do not actually need for their operation standard library often have like a no STD variant, and so they can be used.
Nice, thanks. And
We-
Simonas also has run haste. Yeah.
Yep. Briefly interrupting. So WebAssembly is a little bit special in Rust, in that when in implementing the target, people have decided that it is probably better that we make those standard library functions panic rather than not compile. I don't know exactly what the reasoning behind that was, but uh, typically this will mean that as long as you don't actually call function that access these operating system uh, resources, then it will compile and it will run. But as soon as you do access those system resources, then you will get a panic and the contract will abort.
Yeah,
Also,
that's really
okay.
nice then. Yeah.
Oh, that's interesting. I didn't know about that. Thank you. And okay, for full completeness about compiled targets, there is also the WASM32-WASI WASI target, which is not supported by our blockchain, but is what is usually used to execute WASM32 on hosts. And it executes like with the WASI definition of what the environment would be. Yeah, that's interesting. Like, okay, we can use STD libraries in Rust. Okay, cool. In WASM unknown. So now WebAssembly text examples. So this is just to give you an idea of what WebAssembly looks like. So this is a module. This defines a module. So a module is basically what a WebAssembly, like what a WebAssembly file is. So we define a module that exports one multiply function, and that would be a possible contract call. So not this specific module is not a contract, and we'll see later why that is. But like this would be like a function, a contract call, which takes two parameters, two integer parameters, and returns one result. And then first we get the first parameter, then we get the second parameter, we multiply them, and the top of the stack gets returned as the result. So that's what I was saying, where like the syntax is list-like, and it actually like executes. It actually executes these operations on a stack. So it pushes the left-hand side on the stack, then it pushes the right-hand side on the stacks, and then it multiplies them. So when you take your Rust library, it compiles it to some binary that can also have this text representation. It's always possible to convert from the binary to the text representation and back using the WebAssembly binary toolkit, which, yeah, anyway, we are not going to be needing that, but the idea is like this is what we actually execute. Now, some more complex examples, I will be skipping like the boilerplate outside. When we take one parameter and return one result, and we want to return the minimum between the parameter and 10. So first we push the parameter on the stack, we push 10 on the stack, we do a comparison, and if the comparison was successful, then we return 10, otherwise we return X. That's like pretty standard stack machine based bytecode. So the one thing that may be interesting is how WebAssembly handles switch cases, where basically you have blocks and you can break out of blocks. So here we get one local, so probably a parameter, but maybe a local if the function had no parameter. Parameters and locals are both indexed the same way. So here we had one parameter, so local number 0 was the parameter, and local number 1 would have been the first local, even though there are no locals defined here. So a local can be either a parameter or a local. So we get a parameter, we test if it's equal to 0, and if it's equal to 0, we break. So we go outside of the block, and if not, we set the first local to 42. Nothing very interesting, just so you have an idea of like what WebAssembly exactly is. Like, this way you'll have seen it once in your life and probably never have to come back to it. Okay, so that's nice. Like we can multiply numbers, but like what's interesting actually is for a contract to do things that affect the real world, the real world as defined by the blockchain, but like that affect the blockchain. Just taking a number, having the user pay some gas and then returning a number is not like actually useful for any user. They could just run the program locally, right? So what's interesting is as soon as we actually make use of blockchain abilities, and for that we need host functions. So host functions are hooks into execution. Basically, the WASM binary runs exactly the same bytecode as we were saying, but it also has some system call API. And here the system is our system, the blockchain, which exposes these host functions. So instead of the usual open, close, read, write, etc., connect, bind, system calls that you would find on Linux, instead, you have some host functions that we chose to expose and that we promise will stay valid for all contract execution during their lifetime. So these hooks are things that the WASM binaries are allowed to execute that can have an effect outside of the WASM VM. Because we implement them, they can have an effect outside. So that's the same as when you're running a process on Linux, right? If you run a process, you have access to like the usual x86-64 instruction set, and then you can do nothing. Like you can only make computations. And you actually need system calls in order to be able to have an impact on the file system, in order to make a network request, etc. Everything else is like pure computation and does not have any use. So in the same way, the host functions are the exact list of what a contract is allowed to use. And like, let's say with, I think it was George, I didn't see the face, but I think, George, you were asking about using standard library using about using standard library using crates. We could, if we wanted to, define the web with the WASI API for Near. And that would allow us to say, for instance, like opening a file means looking at this storage key. And then we would be able to actually use the whole REST ecosystem. Now, we probably don't want to do that because like that would be like not optimized for a blockchain use case. So we would need much more thought about it than what I'm saying. But like theoretically, we could say like our blockchain has this interface that is the one we chose to expose, plus the WASI interface. And then the contracts could be compiled with WASM32-WASI instead of WASM32 unknown. And then they could have access to the whole standard library API. And obviously, we would not implement functions such as network access. We would make them always fail. But we could, in theory, like introduce a file system on top of our storage. Yes.
Who maintains this like list? What's available and what's not? Is it on the runtime team?
This list is currently maintained mostly by the contract runtime team and is evolved only through NEPs. So we'll see examples of host functions later and what we add and what we don't. But yes, basically it's like it's contract runtime who deals with that mostly.
I see. Thank you.
So the list of host functions for Neo Core, so on the execution side, the list of host functions is defined in the Near VM logic crate, which is under runtime, and so under maintainership of contract runtime. So this is basically, so I'm saying in the maintainership of contract runtime, it's not really true because there are all like a lot of storage related things in there too. So like, let's say mostly. So the Near VM logic crate is the place where we list the functions a contract is allowed to call. And then the Near SDK exposes these functions in a way that is easy to consume for the smart contract. So it's what I was saying earlier, that like some host function calls are good because we want to reduce the attack surface to the maximum. So we'll have more examples later, but literally just after. But like the idea is the host function we expose is the most minimal API we need to expose in order to provide the functionality. And then everything that is around making it nice happens in the near SDK. And that allows all the making it nice part of it to actually run sandbox. So if there is ever a bug in the part that tries to make the functionality nice to the user, then it will only affect the contract that was compiled with it and not affect the whole blockchain. I've introduced links in the slides, same. There is like the full list as seen by Near SDK and as seen by our WASM VMs that are hopefully the same, even though Near SDK also has helper functions in the list. But basically, we expose, so what happens when we want to add a host function is first, we define what exactly we want to add, the minimal API, etc. Then we implement that into the Near VM logic crate. And then as soon as it's exposed, we have like the protocol version that allows contracts to use it, because it's obviously a protocol change to add a new host function. Then we can expose them from the Near SDK so that smart contracts can start using them easily. So what is there as examples of host functions? So the first examples will be the obvious ones we obviously need. So input allows a smart contract to receive arguments from the outside world. So it's not a host function that any contract in Rust will ever actually use manually. It's used by the X contract proc macro. And it's like magically parsing the arguments and sending them as function arguments. We are not receiving direct function arguments in terms of WASM, because WASM function calls only support like 32 and 64-bit integers, basically. So that would make no sense for a contract that needs to, for instance, get a data structure, like, or parse a JSON, and that would just not work. So in order to do that, we have that input smart host function that allows the smart contract to just say, please put my input in my memory at this place. Similarly, value return allows the smart contract to return arguments to the outside world. So these two operate on raw bytes. So that's what I was saying when I said minimal API. Like inputs takes a slice of n bytes, and value returns takes a slice of n bytes. And that's all they do. So basically, on the contract runtime side, it's hard to get it wrong. And then all the parsing, deserialization, etc., happens from the contract itself. So that's also because in practice, it would be really hard to do the deserialization on the host side, because types do not translate well between outside the VM and inside the VM. But it's also because this way, all the deserialization is done by the contract itself, and so secured by the sandbox. Now, the smart contract can get inputs and return outputs. It can also get information on the accounts involved in the call. So there is like signer account ID, current account ID, and there is a third one, which I forgot, destination account ID or something like that. So there are a few account ID host functions that give the account ID involved in the call. And this isn't necessary for any fungible token things, because basically, like, fungible tokens need to know who is calling the function to know who is paying the token. Yes, I heard something. Oh, I thought I heard.
It was just Marcelo saying it's a predecessor account ID, he thinks.
Predecessor, thank you. Then there are the storage host functions. As I said, like it allows interacting with the storage. And then I mentioned helpers that make things nicer to use. So for instance, Near SDK also has state helpers that are basically like storage, but with a specific key that is state. So that's one place where Near SDK is exposing more than the API we expose from the blockchain, because it makes the life of contract developers easier. And then there are the promise, etc., host function calls that allow creating more receipts So to do cross-contract calls or anything else made possible by creating further receipts, basically. So I'm not going to talk more about that. Jacob already talked about it on January 6th, so feel free to watch the recording if you didn't yet. Okay. Now, there are other things that we are implementing as host functions, and it's not obvious that we need them. Like, we got input, output, storage, and we are able to do cross-contract calls, so what's the matter? It turns out we need other things. So first, there are information that only the blockchain has, like the block index, called block height by Near SDK. The block index returns the height of the block. So that's information only the blockchain has. There's also used gas that returns the amount of gas already used. So we'll talk more about what used exactly means later on. But that returns the amount of gas that has already been used by this contract call. So that's the kind of thing that could be computed by the contract developer, but would be really hard to compute. And it's easy for us to expose it for the contract developer's usage. So why not just do it? And so we expose this very simple function that allows the user to know how much gas has already been used by its contract, so that it can decide like how much gas to send on a new receipt, for instance. And then there are host functions that are like purely for performance. So for instance, we have a SHA-256 host function that computes a SHA-256, and that is needed because basically implemented SHA-256 in WASM would make it much slower, because our WASM virtual machine is not optimizing. So basically, when we execute it, it does not have access to anything like SIMD. It is just like the minimal thing that allows us to run securely something. So executing WASM is safe and it's reproducible and it's all nice, but the issue is it's slow, especially for compute intensive things like computing a hash. So that's the kind of host functions that we can add on an app. So recently we have been looking at adding, I don't remember which signing scheme exactly, but we have been looking at adding a new signing scheme to the host functions list, if I remember correctly. So that's the kind of thing we can add if there is a significant performance benefit and a well-established use case. So we can add them, but we need to remember that there is a cost in that, because if we add a function, we need to support it forever. Because if we remove it, contracts will stop working. So it's not, we could decide to do it, but that's probably not something we'll ever do. So as soon as we add one host function, we need to support it forever, and that's the cost we need to keep in mind when we decide to add something for performance reasons. Yes, I heard someone speak. Beep.
Sorry, I have a two question regarding block index. One is, at this point, when this host function of a block index gets called, is it already determined that this is actually going to be? I mean, is there any case where this the block will change, or is it like either included in this block or it'll be just discarded and just doesn't get included forever?
To the best of my knowledge, as soon as we start executing a contract call, we know in which block it will get executed. And if we don't manage to execute it in time for that block, then we just drop it forever. And
Okay.
if we need to execute it again, then we execute it. Like if we actually need to execute it because it's a receipt, then we will start from scratch on the next block.
I see. And my second question is, how can this information be useful to, I don't know, caller? How do they use it?
So honestly, I don't know. And Sarah, this is the place where I'm sorry, but we will have to make the meeting recording private, because it is very useful for an attacker. So there are other things that an attacker can use, but well, maybe I don't know if we need to make it private actually, because it's not any actual like security vulnerability. But like it's like block index and the fact that we drop receipts in And the fact that we drop receipts when we don't actually manage to execute them within a block means that as soon as we get an undercharging that makes one receipt miss the block, we need to re-execute the whole receipt. And that means that if we have one receipt that takes more than 1.5 seconds to execute, then we will stall the chain, and that's bad. So block index, as well as random seed, which gives a random seed. So like there are also functions that actually have a reason to be there that like have the same behavior. But block index is the kind of primitive that, in my opinion, are more useful to an attacker than to a user. Now, I think some things like probably Rainbow Bridge and other cross-chain bridging probably need to use things like block index in order to validate the cross-chain transactions. But I'm not entirely sure about that.
Sorry.
Would it be a way to measure time? Like, unless there's other better ways to measure time.
So there is also block timestamp, which is like block index but returns the time of the block, which is better, but yes, has the same security issues. But yes, you're right. It can be used to measure time.
So I guess like my natural question would be then, if there isn't too much benefit to users, then why are we even exposing this?
I don't know. So block index in particular, I don't know. Block timestamp is, as said by George, to measure time, and random seed is used because contracts sometimes just need a random seed, though I'm not entirely sure if there are good use cases for random seed, given that the randomness can be controlled by the last valid. Can it? I'm not sure. I think a validator can decide by deciding which transactions to include, probably can affect significantly the random seed of the next block, but I'm not entirely sure about. No, because we are using like verifiable, like pseudo random verifiable function, so we are safe, I think, unless a sufficient number of validators collude, we actually have good randomness. Now, I'm not sure there are. Let's say I cannot think of good use cases for random seed, but I'm pretty sure if we added it at some point, it's because someone asked us. And if we have block timestamp now, my guess would be we first had block index, and then we thought it would be measured to measure time by using the block timestamp, so we introduced block timestamp. And nowadays, block index is probably not that much used, but it's still like there because we need to support it forever, because contracts may be using it, maybe in a place that does not actually even use it, but they may be just linking to it, and then they would stop running if we removed it.
Thank you. I mean, I don't want to spend too much time on this. Just I was wondering if this is like just set in stone that like we have to maintain it, even if there's a like security vulnerability, or if there's any way for us to like somehow lift it to reduce the issue.
So the first thing is, like, I don't think removing it itself would entirely reduce the issue, because we would still have block timestamp and random seed that are probably needed by contracts in the wild. So yeah, I don't think we could reduce that issue significantly by removing it. Now, what we could do what we would be able to do would be, for instance, say it always returns 0. And that would work. But we would still need to have some function that returns something of the same type. Otherwise, contracts, even unrelated, would break. Like basically any contract that did not run all the optimization steps we mentioned probably links to a block index, and so would stop running if we just removed it. But we could make it always return 0.
Thanks.
No problem.
Just to clarify, I'm not George, I'm Vat.
Oh, sorry.
No worries.
Yes, from only the voice, it's hard to tell. So use gas, we talked about it, SHA-256, and we have log functions that allow for logging. So for this, if someone wants to talk about them, I would love to let you speak, because I don't actually know where we log to. Like, it's written in the documentation of Near SDK that that the logs are stored in the blockchain. I don't know what that means, because we probably don't keep it in the chain storage. So yeah, if someone knows what that means, I'm open to hearing more about it.
I think you can see it in the Explorer, but also in Near Social. I believe they will be logged in the developer console.
Okay.
This was awesome, actually, during the hackathon.
Okay, so it logs. So basically, it logs, and then we don't actually store it to the blockchain, but the tools that are developed to use logs allow to fetch them from the Explorer and such. Okay, thank you. Okay, so we are able to do everything, but now we must do everything in a way that does not actually cause problems. Oh, yes, sorry. So not yet. That's the next one. So we can do everything with WASM and host functions, but like, how does it work? Like, how do things to work in practice? What does the code look like? So we have a few WASM VMs that we glue together with the Near VM runner crate. So the Near VM runner crate just like exposes a consistent interface to our WASM VMs. So you will ask, why do we have multiple WASM VMs? And there are multiple reasons. The first one is we need two right now. Right now we have WASMer 2, which is our optimized production VM. So it produces WebAssembly code that is not fast, as we mentioned when we were speaking of SHA-256. The code is definitely not optimized, but it does compile fast. And what we actually need is for code to compile fast and not to execute fast, because each contract call can trigger a recompile because of reasons, basically. Like on each Near Core update, we can trigger a recompile, basically. Like we need to recompile all contracts, and we do that lazily on each contract call. So what we need is a VM that runs fast. Sure, the faster it runs, the better, but that also compiles fast, because each contract call can be a full recompile. And that happens once per contract, per Near Core update, basically. Not really every update, but let's say most updates, or some updates. Basically, every time some constant in the source code changes. And that's when we make changes to the VM. But WASMer 2, which is optimized for production, only supports x86-64 machines. So that means that it does not work on M1 Max. And for that, we introduced Runtime, which is way too slow to compile for production usage. Like, it's literally 10 times slower than WASMer 2, but it supports M1 Max. So for development, we use Runtime as soon as someone uses a Mac. Now that is what we would love to support, but we actually need to support other things because of replayability. So we also have WASMer 0, which is an old VM that is used for protocol versions before version 48. So it was not used since late 2021, but that we need to keep supporting for replayability reasons. And that will make me ask, I think you probably have discussed that with Min protocol onboarding, like what a protocol version is, but there is no recording. So do you actually know what protocol versions are? I will take that as a yes. Okay.
We don't have Min here.
Okay. Yeah, no, but I mean, like, if anyone here does not know, then if people do know, I'm good. And if people who watch the recording don't know, well, feel free to ask on Zulip. So, so WASMer 0, an old VM used for protocol versions before 48. So it's been a bit more than a year now, like a year and a half approximately. But we need to keep it around for replayability reasons. And soon we will have Near VM, which has all the improvements we did on WASMer 2 in the last year and a half. But that will be one more WASM VM, because we basically let's say there are two reasons here. First, we don't want to introduce the concept of a protocol version inside a WASM VM, because that would be a mess, basically. Like, architecturally speaking, the code would become a mess. So we would much rather avoid that. And there are also like organizational reasons that currently make it hard, even if we wanted to do it. When we will have near VM, we will be able, if we want to introduce like protocol versions into it. But my hope is we will have been able to make support on limited replayability. More on that in, I don't know what time it is. Well, more on that soon, on the next meeting just after the end of this onboarding, because this is the topic of today's discussion. So hopefully we will have made progress on limited replayability, and that will no longer be a problem, basically.
Sorry, kind of clarification question. With the limited replayability in place, what will be the VMs we will have to maintain from that?
So if with limited replayability in place, right now we could remove WASMOR 0. So I'd say that's probably a few thousand lines of code as of today, and a good number of tests too that we would no longer need. So today, if we introduce limited replayability, we can remove WASMOR 0. When near VM lands, we would also be able to remove WASMOR 2. So basically, with limited replayability, we would only have to support 2 VMs. And if it's limited to 1 replayability, 2 VMs. If it's limited to 2 replayability, 3 VMs during the times where we are going through a protocol switch, a protocol upgrade. But yeah, we can talk more about that in a few minutes, tens of minutes. I don't know what time it is. And yeah, in a quarter. So we can talk more about that in a quarter, and I think that will be more on the topic then. Okay, so that's how we actually get our code to run. So we have the near VM runner crate that basically takes all the information from the transaction runtime and proxies it through to the right WASM VM. So WASMOR 2, WASM time, WASMOR 0, and near VM, depending on the protocol version and the architecture it's currently running on. So it will run on WASM time on M1 Max, because M1 Max are not supported as validators anyway. And then depending on the protocol version, it will use WASMOR 0, 2, or near VM. Now, the question is, like, how do we get things to actually work? Like, we don't want to allow for a contract to infinite loop and like block our blockchain forever. So in order to do that, we charge for gas. And that's the easy solution, the solution everyone is doing, but the one that actually works. So there are other subtleties to things we do, like Stack Overflow prevention, but the main thing, and the thing users are actually concerned about, is usually gas. They don't care that a contract cannot recurse like 10,000 times towards itself. Usually that's not actually a need for contract developer. What people care about is gas, how much we charge it, how we charge it, etc. So there are different types of gas. The types of gas, so these are names for gas as seen by contract runtime. Outside of contract runtimes, there are other kinds of gas that are used in ways I don't personally understand. So inside contract runtime, we have prepaid gas, which is the gas that the user paid for the transaction to execute. And any gas that it is not used by the end of the transaction will be refunded. And I should have written that non-burnt gas and not non-used gas. Sorry about that. I will fix the slide before uploading. This is non-burnt gas. Then there is the burnt gas, which is the gas that was already burnt when executing the contract. So I will talk more about that on the next slide. But basically, when you execute the contract, you burn the gas while you go through it, and you can also promise some gas. So this is the gas that you attach to further receipts, so using the promise host function calls. This gas gets attached to the receipts, and then the receipts will be able to burn through that gas that has been promised to them. There is used gas, so the one returned by the used gas host function, which is the sum of burnt gas and promised gas. Now, when I said I should have written non-burnt gas will be refunded, because a contract can promise more gas to another contract than the other contract will actually use. So this means that basically you have one contract, it burns some gas, it runs a few other contracts. Each of these contracts burns some gas. So first, the contract cannot burn plus promise to other contracts more than it was prepaid itself. And the promised gas to each of the contracts will become their prepaid gas. And then at the end of the day, when all this has been executed, we sum all the burned gas on all the contract calls, and that is the gas that will actually be paid by the user. All the non-burned gas will be refunded. Yes, I heard someone.
So it sounds like only prepaid gas is a constant, and all the other things are just keep changing depending on where like you're at, right?
Yes, exactly.
And used gas doesn't sound like it is actually used because it includes promised gas. Is that correct?
Yes.
Okay.
You're right. The name is wrong, but it is the name of the host function call, so we cannot change it, unfortunately. So then there is the matter of gas prices. So in our white paper, we promise that we charge gas at, I don't remember what rate, and then we can adjust that up or down, but we have not currently implemented that. But like, let's say in our current white paper, we have that promise about like what the gas price is about. Well, it turns out that we don't actually charge that amount to the user. Even though the formula does compute some gas price, we actually charge for more than that gas price. Instead, we charge for the pessimistic gas price. And the pessimistic gas price is needed to deal with the receipts being delayed and the fact that the gas price can change while the receipts are being delayed. So imagine you have one contract that gets 300 euro gas, and that contract just calls itself. It only recurses towards itself, and it does very little work. That contract will basically take lots of blocks to actually execute. And that means that by the time the last receipt of the contract executes, it's very possible that the gas price will have significantly increased. So in order to avoid undercharging for gas at that point, at the beginning, when the user prepays for gas, we charge the user the pessimistic gas price, which is some formula that basically overestimates the price the user could need to pay in the worst case where the contract calls itself. Now, that's usually not a problem because that amount at 300 euro gas is usually pretty small, even if with the full pessimistic gas price. So users don't care about it, and they will be refunded all the gas price. So basically, the difference between the pessimistic gas price that they paid and the actual gas price of the receipt they executed will get refunded. So they don't actually have to care. Okay, so how do we actually burn gas? Now, that's the one part that contract runtime is most concerned about, because the other things are more about transaction runtime, like where we get delay one receipt and we promise gas to that receipt. So contract runtime itself is mostly concerned about how we burn gas. And there are two ways for a contract to burn gas. So the first thing is when a contract calls a host function call, that host function call will burn some amount of gas as part of its spec. So I know the current, like, most troublesome one of these is the touching try node cost, which is a cost that makes storage operations. Basically, storage operations burn some amount of gas as part of their specification, but that amount of gas is really hard to compute because it depends on the exact state of the try at the time the function call is executed. So basically, depending on unpredictable things, the price of the storage host functions calls can vary quite widely. So these ones are the ones that are most troublesome, but most of the host functions have a set gas price. Like SHA-256 has a set gas price, and that's gas price that stays in stone and will probably never change until we require more advanced hardware and can get the price lower. So that's basically, we burn gas based on the amount of computation that has been performed, or computation or I/O or everything else. That's another topic that we can discuss later in a production discussion slot, probably, whether we should burn gas differently for these different ways. But right now, what we do is we burn gas for any resource we use as part of contract execution. So nothing in the network, because contract execution does not use the network. But as soon as we touch the storage, as soon as we compile, not compile compilation, let's put it aside. As soon as we touch the storage, or as soon as we use CPU to execute the contract, we burn gas. I'm saying we put compilation aside because we charge for initial contract deployment, so the first time we push the contract. But then, as I was saying before, if we update nearcore, then we need to recompile the contract. And that will not really actually be charged for. We are going to charge for it indirectly in the host function call price, but we are currently assuming that that is a cost that is like averaged to 0 over the number of uses of contracts, which may or may not be true. And maybe there are attacks on this front too, where like just trying to make us compile more stuff. I'm not entirely sure. I have not gave much thought about that. But basically, like, contract compilation is not really charged for all the time. It's charged for initially when we first deploy a contract, but then let's say it's only charged for by the stake that is needed to keep the contract on the chain. And that's the only way we charge for the recompiles that need to happen when we have a nearcore update. Okay, so I talked about host function calls that burn some amount of gas as part of the spec. There is also some gas that we burn for each WASM operation that gets executed. So there are two ways this happens: what we do today and what we will do as soon as we get near VM. So what we do today with WASM2 is that we compute the burn gas for the WASM contract execution based on the WASM to WASM instrumentation that was developed by Parity. And that instrumentation charges gas haphazardly. We have one non-security issue about it. I think we've completely burned any opportunity to get that recording public already, so let's speak about it. So for instance, the locals are not charged. So all the work that is done to initialize the locals of a function call is not charged for. Actually, I have not checked whether the latest versions of the Parity instrumentation fixed that. Maybe it did. Hopefully it did. If not, we should probably report that to Parity, because their blockchain would be vulnerable to that attack. But anyway, that gas instrumentation basically has its own concept of metered block. And basically what you see when you call used gas today is not necessarily the gas that has already been used. It can include gas that will be used soon and that has already been charged for by the Parity implementation. So basically, this has a number of troubles, plus it's not actually defined. Like, what it actually charges is not actually defined, and like, it's just look at the code specification. But it's what we do today. This plus memory overflow, stack overflow prevention, and a few other things is called the contract preparation step today. So today, when we compile a contract, first we prepare it, which means we prepare a new WASM contract that also charges for gas, and then we compile that new WASM contract using WASM2. Now, with near VM, we will be lending the work that has been done on finite WASM with Simonas, and this will be our own gas metering. implementation that is based on a strict specification. So what we started doing, and especially Sirena started doing, is write a specification that says what we want to charge and when we want to charge it. And so now, with near VM, used gas will actually represent the amount of gas used until just before the used gas function call. We will also no longer be charging for gas in a WASM to WASM instrumentation, but rather like basically charge for gas directly from WASM when we compile from WASM to x86-64. That should improve performance quite significantly because we will no longer have to have things like re-exports. So let's just, yeah, that's not important, but like for performance reasons, this will probably significantly improve the performance of preparation step, which is basically the only part of the contract that we actually control. Most of the contract is WASM that we do not have any control on. But the WASM to WASM instrumentation, like the gas accounting and the Stack Overflow accounting, are the two things that we actually have control on and that we can optimize on behalf of contract developers because they cannot do anything about it. Yes. I heard someone, or is it just, maybe it's just my Slack saying in 10 minutes we have a meeting? Oh yes, it's because we have 1 minute left. Well, that's good because this was the last slide. So we have 1 minute left. Too late for questions, but if you have something, feel free, and then we can jump to the discussion slots. Well, that was perfect timing. So see you soon then. Bye.
Thank you.